Hello, hello, hello. Let me, hello, everybody. Wait, I don't know if you can hear me. Actually, can I get a quick, oh, good morning. Thank you. Okay, this is all weird. Wait, sorry. I mean, you're not weird. Thank you. Oh, you can hear me. Okay, sorry. Oh, I see what's happening. My chat is, pardon me for a second. I see what's happening on my side. Okay, I just put something long in the chat. I apologize. You'll see it, but that's what was blocking the chat. So I see you now. Yes, I see. Okay. Good morning, Vicky. Thank you. Good morning, Vanita. Good morning, Hudson. I'm saying first to the people that I see pictures. Good morning, Vanita, for the chat. Good morning, Melanie. Good morning, Vincent. Good morning, Mariam. Good morning, Hudson. Thank you for the yes, you can hear me, Melanie. And you get points for that, as you know. Good morning, Vicky. Thank you for the yes, we can hear you, Vincent. Okay. And I apologize for the long thing. I just put in the chat. Please bear with me. You can read it on your own. I just don't want to waste your time with more discussion on this, but I promise you. Uh, anyway, just read the thing in the chat and bear with and forgive me. Well, you don't have to forgive me. Just bear with me. Just know that I'm thinking of you all. I hope you had a good holiday. I was hope anyway. So it's good to see you all. We're just going to keep going with the material now, as the chat thing says. And I think you can't read the chat if I'm going to just keep posting in the chat as new people come in. Um, But we're going to keep going with the material now. We're in the home stretch in a way. I know it won't feel like the home stretch until you have more information. But again, just call me at any time some of you have already taken advantage of this, and I appreciate it. Some of you have already texted me and said I'd like a phone appointment, and then we made a phone appointment, and hopefully it helped a little bit. Good morning, Amelia. Thank you. And you can all do that because believe me, I'm sure for every one of you who is still with me here in the Zoom room and in life, if you're still with me, I'm sure your situation academically is better than you think it is. That's the bottom line, okay? And I'm rooting for you as much as you're rooting for yourself. And those of you who are still with me, if it turns out there's like a borderline case, believe me, you're on the good side of the borderline. And I don't believe in negative surprises. None of you is just going to be shocked with some negative thing. Anyway, whatever. Just read the thing in the chat. You'll understand. But if there's any question, feel free to text me and reach out and we'll talk on the phone. Or something like that. Okay. But for now, therefore, I'm just going to keep going with the material. Um, yes, I'm going to keep going with the material. Um, there's there's no new homework. The most recent homework that was ever put in your pile was the work done by constant forces. Like technically that was due a while ago, but it was sort of prematurely due. So you're still all very welcome to do it, um, to get all the points, etc., to redo it and get all the points, etc. But now finally I'm going to start talking about that, so that you can do that homework or redo it if you wish. But also, I'll tell you. So I'm starting new material now, is what I'm trying to say. And stop me if I'm not being clear. I am a little bit like something, something. The material I'm going to start now, which is the topic of work, physics work. Um, that's the material I'm going to start now. It ends up being related to your sort of last couple of labs in the course, but also and I'm going to explain it now for the first time. Like, yes, you've been asked to think about it in the context of homework and so forth, but everything I'm going to say now about this new material concept of work and energy in physics, I'm saying fresh. I will explain it now in my terms without any assumption that you have thought about this before. You might have, but so you haven't missed anything, is what I'm trying to say incoherently. I'm going to explain the concepts of work and energy, or start to explain them now. Again, for anybody who just like joined the Zoom, it's like a new topic. It's one of our last topics of the semester. And let me be very clear about this Oh, I love it. Oh, that's so nice. Okay, Vincent. Wow. Um, 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 this topic of work and energy, which I'm about to start explaining now, for what it's worth, yes, you'll want to know it for the final exam when we finally get there, and you'll want to know it for your last labs and all of that. But also, quite frankly, it's really a transition to Physics 204. I mean, I hope to personally see you all in Physics 204, but even if, and I think I should see most of you in 204, but whether you have me or somebody else or whatever, Physics 204, picks up where Physics 203 ends. And this last topic of work and energy and and some of the calculus implications are very, very relevant to 204. So I guess if nothing else, what I'm saying before I dive in is whatever notes you take or whatever attention you pay to this last topic, I would strongly suggest that you save your notes, set them aside for next semester, because they'll be very helpful then. Okay, I'm looking at the chat and so forth. Okay, hold on. There's things in the chat. Bear with me for a second, and then we'll get rolling again. I see. Sorry. Hold on. Um, sorry, I'm looking in the chat. Oh, wait. Okay, and there's a lot happening in the chat. Forgive me for a second. Hold on. Hold on. First of all, just for anybody who just joined, I just put something in the chat that's not just for anybody who joined in later than when I put it in the chat. But hold on, but there's also other questions in the chat. Let me answer publicly. Sorry, I'm getting myself disoriented. Sorry. Okay, right. So someone's asking in the so I so sorry, you can see I'm a little bit. What I want to get to today, what I'm trying to say is we're about to get to this sort of one of the last, sort of the penultimate topic of work and energy. It's a big topic. It's relevant for life. It's relevant for Physics 204. The midterms I wish I had more to say about right now. Please just see the chat for my overall recognition or acknowledgement or apology or update on that. But then someone just asked in the chat also about the final exam. That's a very fair question. Um, so I want to acknowledge that. As far as okay, I can tell you this quickly. Maybe I can tell you the full official details on Wednesday now that you're raising it. I can tell you that with the final exam, for good or for bad, it's the same format as the midterm, meaning you're going to take it home. Just like you, so we can sort of say this officially right now. You're not going to take it in class on one of those exam days. You're going to have a bunch of days to do it at home, for good or for bad. So, yeah, we can do this right now. Sorry, since someone's asking, and it is fair. Um, your exam, let's just do this right now. Sorry. And I'll put whatever I'm about to say, I will put in Google Classroom so it's official and clear. But since someone's asking right now, please tell me, please remind me, since I don't tell me the very last day of final exams officially is what? Is Tuesday or Wednesday could someone put in the chat? It's Tuesday or Wednesday or what day is it? The very last day, or is it in the chat? Wait, are we? I don't see the chat. Can anybody, or if you, well, what I'm trying to say, you can confirm, we can figure this out right now. What I'm trying to say, because I'm a little bit something is generally speaking, what we do in physics is we make the final exam due the Monday of the final exam week of the last. So like if your final exams, we can, if you, I can look this up, but it might be better if you do. Say if final exams end Wednesday, December 17th or something like that. In fact, I think that's actually, if final exams end Wednesday, December 18th or something like that, then what I'm saying is your final exam would be due Monday, December 16th. It would be posted Thursday, 15, 14, 13, the 12th. I'll write that in the chat in a minute if someone can confirm that my dates are not crazy. Or maybe, and if only one person cares, then we won't get bogged down in this now. But I mean, it seems like a relevant question. All right, I'm going to write. Could someone just confirm when? Thank you, Vicky. Okay. Thank you, Vicky. Sunday to Saturday. Thank you, Vicky. Okay, and you get points for that. So Vicky is saying that final exams are the 15th to the 21st. And the 21st. Okay, hold on. Let's just do yes. Oh my God, the 15th to the 20th. Well, all right. Then I'm gonna. You know what we're gonna. All right, I'm gonna Sunday to Saturday, 15th to 21st. All right, that's a little different from what I thought. All right, then I may have to do this officially. Bear with me for a second, everybody. I apologize, but this is a fair question. I mean, obviously, it's an important question, so let me do this right. Hold on a second. This class meets. Okay. Okay. No, I'm glad you're asking. Sorry to sound like this. Okay. Okay. I'm going to put this in the chat right now. This is it. I'm just looked again for anybody who's tuning in. I'm talking about someone's asked about the final exam. It's a totally fair question. Especially in this class where I know not everything is obvious. So I'm going to say the answer. I'm going to put in it. I've just looked at the official, like I've looked at where our official physics, where our exam should be if we did it in class. So I'm trying to be fair, so I don't want to do anything unfair or do or go against, like, obviously the exam schedule is designed so that your exams are distributed uh, throughout your own schedule in a way that's manageable, right? So I don't want to violate that. I don't want to like, so your exam would be Monday. It would be the first day. It would be the 16th, according to the official schedule. Yours would be Monday if it were in class, and the other section would be Wednesday if it were in class. But the way I do it is it's take home and you're all out to work together and all that kind of stuff. So I think the fairest thing I can do, and also the most manageable thing for me, since as you can see, it takes me a while to do these exams, I'm going to say right now that your exam will be due Wednesday. Okay, I'm writing it in the chat right now. Like it'll be posted before, like probably the Friday before, maybe even the Thursday before. It'll be posted before the weekend. But so if you want to turn it in by Monday and get it out of the way as though it were an in-class exam Monday, so you could do it, you can, obviously. But if you want to take till Wednesday because the other section's going to do that anyway, like you, so anyway, for good or for bad, I'm writing it right now. I'll put it in Google Classroom. Your final, and I hope, but just acknowledge whether this is clear. Okay, so um, first of all, as long as that question just came up, could you guys could you raise your electronic hand or something to confirm that you see this posting in the chat about that your exam, your final exam will be due. But thank you, Vanita. Thank you, Hudson. Oh, and thank you, Hudson. Got it. Thank you, Vicky. Totally noted, you thank you, Vicky. Okay, and I think because one of you was what? Thank you, Jean. Okay, thank you, Annie. Okay, so and again, of course, I'll put that in Google Classroom, and this will apply to the other section as well. It's partly designed so that you guys have the same situation as the other section, so that you can help each other, and also so that someone doesn't get an advantage just because you happen to be meeting at this time. Okay, so so it'll be thank you, Melanie, for clarifying. It'll be posted the week before. What I'm not sure is whether it'll be posted Thursday or Friday. It'll be posted before the weekend. Like you'll definitely have the weekend to do it if you want. I don't know for sure if I'll post it Thursday or Friday. I'll update that in Google Classroom, but no later than Friday of the weekend before. So you'll have the weekend to do it, and Monday, Tuesday. Okay. Does that answer, Melanie? Is that or just tell me, Mel? Yes. Okay. Thank you. Great. Okay. All right. So that's the deal with that. Okay. And I can tell you right now also, I mean, this has happened before, because I know it's causing stress to still not know what you did on your midterms. Like, I get that. I can also tell you now that generally what I do, especially in these circumstances, is by the time you get to your final, it's meant to help you. Like, what I basically what I often do, am I going to say this right now? Yes, I will say this. I'm going to, I have to count both. I can't discount an exam because we don't have enough exams to do that. Like you both will count, but whichever one you do better on, I will count higher, more. I will weigh the one you do better on slightly more than slightly. I will weigh the one you do better on more than the one you do worse on. Therefore, if it turns out you did well on the midterm, then you won't be able the final won't wreck your average. If you did well in the midterm, then you did your hard work, and the final will just be there to hopefully seal the deal on your average. But if you, it turned out you struggled on the midterm and you didn't have a lot of time to think about that or process that or improve yourself to the final, then if you can do better on the final, you understand what I'm saying. I will do that. I will weigh the better of your two exams more than the worse of your two exams. I don't always do that, but I have done it in the past and I will do it this semester. I hope that's clear. Um, so view the final as an opportunity. Anyway, all right. So hopefully this is all clear. So I want to go on. Okay. Okay. So if we're all cool, I'm going to go on to new material now, at least for a bit, just to shift gears. Are we cool if I go on to new material? Is this cool? I mean, are we clear? Oh, speed up. Okay. All right. Fair enough, Annie. Thank you. All right. So here we go. Okay. Thank you, Vicky. All right. So totally new concept. Here's the concept. Okay. Here's the statement of today. I don't think you can read the last word. What I'm saying here on purpose, I am right now, we're talking about work, but I'm starting the topic of work by defining I am defining a little bit of work to be the dot product of a force vector with a little displacement vector. Okay, so I'm in a way, so I'm saying a little bit of work is the dot product of a force vector with a little displacement vector. Apparently, I'm using those triangles in a way to mean little. Now, a couple of things. First of all, what do I mean by little? Like, how crazy is that? What do I mean, little bit of work? Of course, I'm going to explain. The other, well, okay, so let me write down. So, first of all, what do I mean by little? And also, well, more specifically, like, why do I keep using that little triangle? What's that all about? But also, what do I mean by dot product? That's like a thing. Honestly, it's a very big thing in Physics 204, but I've never discussed it, but I'm going to discuss it now. It's a math thing. Okay. So first of all, let me just so dot product is a certain way. I'm going to go backwards a little bit for a second. A dot product, I'll explain in more detail in a moment, but a dot product, in short, is a way of multiplying two vectors. It's a specific way of multiplying two vectors. I'll get into that in a moment, but it's a way of multiplying two vectors. So on the big picture, what I'm saying right now is a little bit of work is the product of a force vector with some kind of displacement vector. But why do I keep saying little? And why do I keep using a triangle to connote little? Here's what I mean. Well, interesting. Wait, I see the chat. Hold on. Good chat. 1 second. Let me just read. Almost, kind of. 1 second. Okay. Uh, wait, I'm seeing the chat. I'm seeing the. Okay, okay. I'm seeing the chat. Very good chat, Annie. Great questions. I'm going to slightly disagree, actually, but like great proposals. So, what I really mean by delta from now on, I'm going to use delta. Well, I mean the same thing that you always meant in math classes, all of you, when you said like delta y or delta x, as in rise over run, delta y over delta x, right? Whenever you said, whenever you said like delta y over delta x in a math class, and you meant slope, you meant rise over run, like like delta y always meant y2 minus y1, right? And delta x always meant x2 minus x1. It seems obvious. So delta means difference, right? But actually, what we might never have realized in a math class before is whenever we use delta in a math class, we do mean difference, but we mean, even though the difference might be really, really small, like it might be on a graph, it might be this like really small rise or this really small run, even though it's a really small difference between two values of a variable, of any variable, I'm calling it z right now. We use delta when the difference between the two variables, no matter how small it is still large enough to be finite, to be measurable, to be countable, right? So when we say, so that's why when you say delta y in a math class equals y2 minus y1, when you say delta y equals y2 minus y1, you literally mean that. You mean that you can identify y2 and you can identify y1 and you can like subtract them from each other and get like a number. So so um delta in general, when you use it for any variable in math or physics, so I'm calling z. Z means like any variable at all, whether it's x or y or whatever. We use delta when something is might be small, but it's still finite. Now, I still haven't addressed Annie's question or exact. So part of what I'm saying is delta means finite, but it also means small. Well, small compared to what? What do we mean small? Well, here now comes the Annie question, and here's what I mean. Delta Z is what, and again, I'm right now saying Z to emphasize it could be any variable. Like, obviously, I'm going to go back in a minute to the physics of X. But right now, I'm making a math point and saying if Z stands for any variable at all, then when you write down delta Z, you mean a small but finite, like calculable, measurable difference between two values of Z. But if you write down dz, that also means difference, right? Delta D, Greek letter D stands for difference, but lowercase d stands for a special kind of difference, which means a difference that is so small that it's infinitely small, so small that it's something, it's not zero, but it's too small to measure or to count or to quantify. So when we switch from delta z to dz, we're switching from something called a difference to something called a differential. Right? This is like a big warning. You might see where this is going. I'm trying to emphasize right now that delta is like the transition into what you recognize ultimately as calculus. We're starting now, like we've seen some calculus before with derivatives. Now we're going to see some calculus in a different way now. And I'm trying to emphasize well, I'm just trying to emphasize this right now, that a delta z means a small but finite difference between two variables. Dz means an infinitely small difference between two variables, known ultimately, therefore, as a differential, not a derivative, but a differential. A differential is an infinitely small difference. Okay. And so now, finally, to loop back to Annie's question, okay, I'm going to write, here's the math point. Then on the next page, I'm going to write the physics point, and then we'll see if it actually does or does not address Annie's question. And seriously, because I think her question's a good one. What I'm trying to say now is from now on, if I say delta z about any variable, what I really mean is it's finite. It's a finite interval, finite measurable difference between two variables of z, but small enough. So it's big enough to be finite, but it's small enough that any other variable that is related to z doesn't change noticeably in that sized interval of z. Like, what? Like, what am I saying? I'm saying physics wise, here's what I mean. Okay, to bring this full circle, when I say Right now, I'm defining a small amount of work. Okay, I'm saying right now in physics, we're defining what it means to do a small amount of work. And I'm ultimately going to say a small amount of work is the product of a force vector, a certain type of product of a force vector with a displacement. Let me say that again. A small amount of work in physics is the product. Let me say it again. A small amount of work in physics is a certain kind of product of a force vector with a small displacement vector. What do I mean by a small displacement vector? What do I mean by delta x vector? Notice that is a vector symbol there. What do I mean by a small displacement vector? I mean a displacement vector that is so small, that is big enough to be finite, but small enough to not allow any variation in the applied force vector. That's my restriction right now. So I'm saying right now that what we are envisioning right now, and what we envision in that homework assignment that some of you could still totally do and some of you have done, what we're envisioning right now is situations where something is pushed or pulled through a small displacement. And if we multiply the amount of the push or the pull times the displacement, we get an answer that we call work. But we're restricting ourselves right now to cases where the displacement is small enough that the amount of the push or the pull and the direction of the push or the pull don't get a chance to change much during that displacement. So to circle back to Annie's question, which I'm going to look at more carefully now, like little in this case does means a little bit bigger than zero. If it were literally zero, then we'd have nothing to multiply by. It's a little bit more than zero. In fact, it's enough more than zero that we have a number to work with. But it's marginal, like she says. Little means marginal. Not if marginal means it doesn't matter, then I don't agree with that. I don't think she means that. But marginal means in this case is the displacement is marginal enough that it doesn't allow the force to change. So in super big terms, I'm sure I've lost some of you now because I'm like over talking this. I'll move on in a second. I am saying, just to repeat, I'm saying a little bit of work, a little bit of work, a little bit of work is defined to be a force vector times a little displacement vector. Um, okay, so the summary of what I'm saying right now is that work is the product of force times displacement in the case where the displacement is small enough to allow us to pick one number for the force. That's basically what I'm saying. I mean, that is what I'm saying. I'm going to pause. So what I feel that but I've said too much, or what I feel that I've defined so far is this business of little and the triangles. That's what I'm trying to explain right now is why I'm using those triangles to mean little. What I mean by little is small but finite. What I mean by small is small enough that there's no variation in the F. That's what I feel like I've explained so far. What I have now to explain is the dot in between the two vectors, like what this dot product is. But can I just ask Annie or anybody else, is this clear so far? Even though, I mean, I'm sure Annie's going to say speed up and that would be fair. But does it make sense so far? I mean, you got it. Okay. Okay. Great. Thank you. Okay. Okay. Great. Thank you. Okay. So now I'm going to do one more thing. Now I have to get a little bit more detailed now. So I have to explain the other piece now. So what do we mean by the dot product? Okay. This is another math point now, right? I mean, this is, I'm going to make a math point here that of course, applies to the physics. Excuse me. So, in general, ooh, Hudson, very good. Wow. Okay, first of all, points, 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 total acknowledgement of great contribution. Like, seriously, right on the topic. Now I'm going to modify slightly. So Hudson just brought up the issue of perpendicularity. That is totally the issue. I'm going to go the other way and talk about parallelism. But yes, the whole issue of dot products, the whole issue that we're about to address is the extent to which any two vectors are perpendicular or parallel. I mean, perpendicular is like the opposite of parallel. So the more parallel you are, the less perpendicular you are, and vice versa. So that is totally the issue, what Hudson just said in the chat. Now I'm gonna sort of come at it from the other direction. I'm gonna talk about parallel, but yes, that's awesome, Hudson. So here we go. Let's assume that we have two random vectors. So again, I'm talking math now. Like I'm about to apply this to a force vector and a displacement vector, but let me make this general point first. Let's say you have two random vectors, A and B. Well, what we've never discussed before, we've talked about adding and subtracting vectors, right? That's like your whole first exam, like placing them to tail or tail to tail, whatever, and you divided them into components in order to add or subtract them. But what we've never talked about is how do you multiply vectors? What does it even mean to multiply vectors? Well, it turns out there's a number of different ways to multiply vectors. Uh, there's a number of different ways. Um, and we're interested in one of those ways right now. Excuse me for one second. Just kidding. Sorry. Okay. Wait, oh, there's something else in the chat, or that's the same. Okay, okay. Right. Okay. Um, okay. There are three ways that multiplication can be performed if you're in the world of vectors. First way we've done a million times without ever thinking about it necessarily, which is you can take a vector and you can multiply it by a scalar. And we actually do that all the time without necessarily thinking about it. When you multiply a vector by a scalar, you're taking an arrow and multiplying like, what is a vector? A vector is an arrow. It has length and orientation. It has magnitude and direction, right? So if you take a arrow and you multiply it by a pure number, you're just stretching or shrinking the arrow. Um, so whenever you do that, you produce a new arrow just of a and in fact, if you take an old arrow and you just multiply it by a pure number, you get a new arrow that points in the same direction as the old arrow, but it's just longer or shorter. So you just scaled up or you scaled down the old arrow. That's actually why pure numbers are called scalars. They just scale vectors, if that makes sense. So if you ever multiply a vector by a scalar, you just get a new vector always. And we've been doing that tacitly without even thinking about it, like every time we make a vector. Okay, but then the more interesting, and that's relevant for physics 204, by the way. Like all of this is, you know, preserve this somewhere in your brain for 204. But where it gets more exotic is you can take two things that are already vectors and you can multiply them together, but you have a choice always in math and in physics as to whether to multiply two vectors in a manner that produces a pure number or in a manner that produces a vector. That's a choice. Just like with any two, and you make the choice based on the physics needs. Like literally, like just like with any two numbers in life, like the number two and number three, you could choose to add them and get five, or you could choose to multiply them and get six, or whatever. Like there's different operations that you do for, and why you would choose your operation based on the context of what you're thinking about, like the word problem that presented itself to you. So same thing, any two vectors could be dotted together or crossed together. When you dot two vectors together, you're multiplying them in a way that produces a scalar, like necessarily always. If you cross two vectors, which is a different operation, you relate them in a way that produces a vector. So like, how does this work or what does this mean? Well, the one that I'm going to zoom in on now, the one that we're interested in for this physics context now is the dot, the first one. Okay, now this all relates to the whole Hudson observation here. If you're trying to multiply two vectors, if you're trying to relate two vectors in a manner that would produce a pure number, what you're really asking is how, to what extent do these two vectors actually share a number line? To what extent can we say that they're lying along the same number line? To what extent can we treat them as pure numbers? In other words, when you're trying to get a scalar product, a scalar result from the measurement of two vectors, what you're really trying to ask is how parallel are these two vectors? Because if two vectors, for example, were purely parallel, if you had a vector, if you had a displacement of 3 meters pointing to the pure east and a vector of 5 meters pointing to the pure east, then you really have two arrows pointing along the same number line. You really have the number 3 and the number 5, and the product of the number 3 and the number 5 is the pure product 15. Like, in other words, it doesn't matter at all that they're vectors. They're just numbers lying in the same direction. You wouldn't have to take into account it, right? So the more parallel two vectors are, the less direction matters, and the more they would produce a pure product in the same way that regular numbers on a regular number line would. So in other words, very quickly, looking at the time, we have 20 minutes. What I'm saying here then, if you have any two vectors, the dot product of the two vectors is a number. Like no, so you have two vectors, vector A and vector B. To dot them is to take the length of one. Let's make this. When I say A without any arrow over it, or if I say B without any arrow over it, I mean the magnitude of the vector V, right? If I like, notice I'm being trying to be careful here. When I put an arrow over a letter, it means the full vector quantity of that letter. If I get rid of the arrow, it's not a typo. It means I'm just talking about the size of that vector, the magnitude, the right, the scalar value. So to dot two vectors is to take the length of one vector, multiply by the length of the other vector, and then multiply by the cosine, specifically the cosine of the acute angle between the tails of those two vectors. Why the cosine? Because cosine is that funny thing that gets smaller and smaller as an angle gets bigger and bigger in the first quadrant, right? Like always remember sine super, cosine crappy, or sine super, cosine counterintuitive, if you like. Or like sine does what you think it would do. Sine of zero is zero. Sine of zero is, if you're going to memorize anything from the unit circle or anything like that, always memorize sine of zero is zero. And then as the angle gets bigger and bigger, the sine gets bigger. That's the one that's like super and natural, the way you would, it's simple. Cosine is crazy, is counterintuitive. It's not really crazy. It totally makes sense ultimately, but cosine is the one that does the opposite. The cosine of zero is one. The cosine of 90 degrees is zero. Cosine gets smaller and smaller as the angle gets bigger and bigger. So cosine is the operation that really measures parallelism. If you think about it, when the angle between two things is zero, the cosine is one. So if you had two vectors that were totally parallel to each other, the dot product of those two vectors would be the length of one times the length of the other times the cosine of the angle between them, which would be one if they're purely parallel. So two purely parallel dot vectors would have a huge dot product. In physics terms, well, let me say the opposite, and then I'll say in physics terms, and then I'm going to pause. The opposite is if you have two vectors that are, now this is Hudson's point again, like again, I'm saying it from the opposite perspective of what he said, but it's the exact same topic and the exact same analysis. If you have two vectors that are perpendicular to each other, no matter how big they are, their dot product, if they were purely perpendicular, their dot product would be like some big number, the length of one times the length of the other times the cosine of the angle between them. And if they're perpendicular, the angle between them is 90. So the cosine would be zero. So no matter how big the vectors are, the dot product would be zero. What does all of this have to do with physics? I'm going to say this quickly. What I'm saying is work is a scalar quantity. One joule of work equals 1 Newton of force times 1 meter of displacement. 1 joule of work is defined to be 1 Newton of force times 1 meter of displacement. But in what sense? In what context? It means, example, this is an example. So this is a mass. Say there's a block on the floor and I push it with a force. I'm pushing it with a force of 100 newtons and I'm pushing it across the floor horizontally at five. Oh, that's my hand, I guess. Wait, I think that's my hand. Oh my God, that's so confusing. Um, Say I'm pushing this box across the floor at a displacement of 5 horizontal meters. but I'm pushing it at an angle of 60 degrees as measured from the horizontal. Like, why would I do that? Just because it's easier, because I don't want to, because the box is on the floor and I don't want to crouch all the way on the floor, like my knees hurt, whatever. So I'm just like standing up above it and pushing down at an angle, right? Just because that's easier leverage wise. So I'm pushing at this angle of 60 degrees measured from the horizontal. And I'm pushing with a force of 100 newtons. We would say, we would say that the work I do would be 100 newtons times 5 meters times the cosine of that angle 60 degrees. In other words, the work I would do in the end of the day would not be 500 joules, would be 250 joules. I'm assuming that because the cosine of 60 is 1/2. You could do that on the calculator. Because what we're really saying here, what we're trying to say now, physics, okay, so the math is a dot product only takes, what the dot product is really doing is it's saying, I want to multiply these two vectors. I want to multiply the 100 Newton force vector by the 5 meter displacement vector. But I really don't want to multiply all of the 100 newtons, because if I were to draw a triangle, if I were to look at this 100 newtons of force, only some of the 100 newtons are going directly into horizontal displacement. Only Fx, the horizontal component of the 100, is directly affecting the box's horizontal displacement. The rest of my effort is shoving the box down onto the floor, and that's not helping it at all displace. It's like wasted. Or maybe it's even bad. Maybe it's even increasing friction for all I know. So what physically we're saying is we're going to use a dot product when we multiply force times displacement in order to calculate work, because what we want to say is only the component of force that is parallel to, that is matching the displacement, should be included in our calculation. So we're, strictly speaking, we're really saying 100 cos 60. We're saying like the horizontal component of 100, or the component of 100 that matches the delta x, is all that's being multiplied. So we multiply 100 times 5 times the cosine of 60, which ends up really saying, which ends up meaning 100 cosine 60 times 5, which ends up being not 500 joules, but 250 joules. I'm going to pause for a and take it to the extreme. Well, wait, I'm going to pause for a second. Just raise your electronic hands if that's clear. Does that, that's what I'm saying is the definition of work, of a little bit of work. That's what you do as long, oh, super clear. Wow. She said, thank you, Annie. That's like the nicest thing ever. Okay. And thank you, Mariam. Thank you. Awesome. Okay. Actually, that means a lot coming from both of you. Seriously. Okay. I'll take it. Thank you. Okay. I also know that Annie secretly, when she says super clear, she means move the heck on. Yeah, but fine. No, I'll take it. I'll take it. Okay. So if that's super clear, that's great. And I'm going to keep going for a second. The reason I was rushing, I just also want to admit, um, I was going to do this class, but I won't because we're running out of time. Please remind me next class. You see in their Google Class, I would like to give you time to do teacher evaluations. I'll admit also they always make me super nervous, but you know why they make me super? Because they do matter. Just so you know, total sidebar right now. I've been on the committee for years, like since I've been on the student evaluation to faculty committee, the college committee for years, working on improving that evaluation form, working on like how it gets to students, how it's used by administration. Let me just tell you quickly, sidebar, that form matters more than you think. I know that you think it doesn't matter at all. And I know you feel powerless over faculty. And yes, you don't have as much power as you should have, or as you, etc. But I am also telling you the forms matter much more than you realize, so much more that they make me totally nervous every time. So I just sidebar, you'll notice in your, I don't want to see your forms at all. Like I don't want to, and I can't. But you'll notice in the Google Classroom, as long as you do your forms, as long as you fill out a form, one for lecture and one for recitation, because technically they're two different classes, even though you could fill out the exact same content if you want or whatever. As long as you fill it out and just show that you filled it out, you get 10 points for each of those forms. If you fill it out at any time, you can get 10 points, but I will give you time. Please remind me in class next time, like Wednesday. I will give you time to fill them out so that they get filled out. Again, I won't ever know what you said, but believe me, people know what is said in general. Um, anyway, so just remind me next class. And you can do it before if you want, and then you can use the time during next class to do other things. But remind me next class, I'll give you time to fill them out, and I want to give you the proper 20 minutes. And since we don't have that now, I'm going to keep talking. Just remind me next time, please. Or fill it out on your own time at home. Either way, you'll get the 20 points, blah, 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 blah. Now I'm going to keep going now then, if this is clear, because there's one step further. Okay. Okay. So with 10 minutes left, now oh wait, and there's something in the chat, or maybe I already saw it. Hold on one second. Wait. Oh, no, okay. So again, what we have right now, the summary of what we have right now, even though I haven't done like a lot of examples or anything, a little bit of work, a small but finite amount of work is the dot product. Oh, in fact, so let me sum. So in summary, I'm saying so far, well, I guess delta W equals F times delta X times cosine of theta. That's really the summary of everything I'm saying so far. But the cosine theta is the key. The summary of if you've been tuning in and out or it's just getting to be too much or not enough, everything I just said so far is summarized by the cosine theta. It's saying a joule of work is a Newton of force times a meter of displacement, but you have to take into account the angle between the two. If there's no angle between the two, then great, fine. It's straightforward. But if there's any angle between the two, you got to multiply by the cosine of the angle. The cosine then represents like a factor, like a percentage factor. The bigger the angle, the smaller the dot product. Okay, that's what we're saying so far. But now the issue is, okay, that's all what you do if the displacement is so small that you have a clear number for F. What if the displacement is big enough that F is varying? That's the issue. And that's what really gets us into Physics 204. Well, here's the answer. Okay, one thing I may have said before in other words is we believe in physics that at least when it comes to forces, the whole is equal to the sum of independent parts. And we don't believe this about everything, but we believe it about forces. We believe, like this whole concept of net force, we believe that if I push you with 3 newtons of force to the south and somebody else pushes you with 5 newtons of force to the north, we believe that the net force on you is 5 north plus 3 south, or in other words, like say 5 minus 3 equals 2. We believe that the net force, pardon me, the net force on you is 5 minus 3 equals 2. Now you might say, well, duh, like, why is that even worth saying? Like, duh, of course. Like, you add the forces, you get the whole force. What we're really saying is that each force acts on you, and that each force acting on you contributes to a whole as though no other forces were there making any other contributions to the whole. What we're saying is the forces don't interact with each other. We're saying that you can push me and somebody else can push me, and each push goes into a bucket and gets combined in the bucket and gets a whole push on, makes a whole push on me. But the fact, what we're saying is the fact that while you're pushing on me is not affected by the presence of somebody else pushing on me at the same time. We're saying that each of you can push on me, but you can't push on any other push. Again, maybe that's a mouthful for some of you, but that's what I mean when we say the whole is equal to the sum of independent parts. Each part makes its contribution, and the contribution is not interfered with by any other contributions. That's what we're really saying. Okay, now not everything is like this in life. Waves are not like this, but forces are like this. So, what does that mean? It means what I'm saying is, with 5 minutes left, I'm saying, say you're pushing that box along the ground and you want to know how many joules of work you're doing while you push the box along the ground. Say it's a more complicated example where your push is getting bigger and bigger. What, like say you're pushing the box for a far enough displacement that your push is getting bigger and bigger while you push it, or smaller and smaller, or changing direction or something. What will we do then? Luckily, because we believe superposition, because we believe the whole is equal to the sum of independent parts, we actually can analyze this in a somewhat natural, straightforward way. We can say, if you're pushing the box through a big journey through which the force vector is changing a lot, as long as we can divide your big journey into a lot of smaller journeys, if we could divide it down to a small enough level where we have a bunch of small journeys, each of which has its own little force number, force vector that applies, then we could say the work for the whole journey is equal to the work for the sub journey number 1 plus sub journey number 2 plus sub journey number 3. Right? I mean, it sounds so obvious. And well, I don't know if it sounds obvious or not, but the fact that it's true makes our life manageable. In other words, we can say, and I know there's 3 minutes left, we can say the sum, like the total amount of work, a big amount of work. Notice I'm not using the deltas now. I'm saying, well, I'm not yet, the big amount for a big amount of work. Now, don't be intimidated. Well, please, well, you can be if you want, but remember that big sigma sign from math class. right? We're saying, oh, okay. I'm looking at anything, and this may be where we wrap here. I'm glad. I'm saying, are you saying that given an extra? Yeah, totally. Wait, so to 100, 1 second. I'm just gonna write this in case anybody tunes in the last 2 minutes. Yes, Annie. Um, and since we only have 2 minutes, yes, yes, yes. So, and in a way that sounds like so duh, right? It all like well, yes. So I'm saying like if you so yes, I don't even know how, yes. So yes. I okay. All right, great. So now so, in other words, this would be the end of the story. With 1 minute left, this would be the end of the story. From here on in, I'd be saying, like, okay, so if you first push a box with a force of 10 newtons, and then you push a box another meter with a force of 20 newtons, and then you push a box another meter with a force of 30 newtons, you would just do 10 times 1 plus 20 times 1 plus 30 times 1 and add them all together, and that would be the total work for the whole thing. The only question is, and we're going to end on this, I know we have 1 minute. The only question is, that's not even handwriting. And this is what we're going to pick up on Wednesday, and we'll do the evals. Like this is the end of the story. Just add up the but what if it's real world? What if this is real life where people don't push a box and you don't go like and then and then it's not right. It's not like a strobe light in real life. Generally speaking, what would happen is you'd push a box and you would smoothly vary your force, right? You wouldn't jump like that. It would just like continuously vary from 1 Newton to 1.1 to 1.2 or whatever, right? It would vary. Well, it's 1205. So what would we do in that case? What would we do in that case is we'd have to go to the limit. And this is where we'll pick up. Don't be intimidated. I'm going to pick the, I'm not, we'll pick this up on Wednesday. But in the true, ugh, I'm ending right here. In the true case that we really care about, uh, we'd have to add up these situations in the limit where each displacement was so small that it was infinitely small, right? And that's called a dx. And that's what's going to get us into integrals starting Wednesday. But that's where we'll leave it for right now. Okay, thanks. So you guys have been very patient in general. You're being very patient all over the place. I really appreciate it. We'll just keep going with this Wednesday. Keep on keeping on, and Quark bless America, everybody. And I'll be here for a couple minutes if there's any questions or anything. I'm stopping.